Hello, so in this problem we are studying interference points along a big circle. So we're given 2 point sources S1 and S2 which are in phase and separated by a distance d equal 1.5 lambda. So this distance d is 1.5 lambda, where lambda is the wavelength of the sound waves emitted by these two sources. And of course these are identical sound waves which are in phase. And we're studying different situations and different points at which we want to know what kind of interference we will have between these two emitted waves. So in figure B, we have our first situation. So the wave is traveling along the path S1, P1. This is our first wave. And the second wave is traveling along S2, P2, sorry, P1, with P1 lying on the perpendicular bisector of S1, S2. In figure C, we have the second situation. So we're studying a point P2, which lies along the line S1, S2. And we are interested again in studying what kind of interference we have. And in figure D, we have this big circle, and S1 and S2 are right here. And we want to study what kind of interference we will have along this whole circle. We'll get back into the details when we reach this situation. But let's first get back to our first situation where we're studying this point P1. Now, the first thing we can notice here is that the path length difference between the two sources is going to be equal to 0, because S1 P1 is equal to S2 P2, because P1 is equidistant from the two sources because it lies on the perpendicular bisector of the line S1, S2. And this means that the waves arrive exactly in phase, and they will undergo fully constructive interference since the path length difference is 0 between them. If we check our second situation, on the other hand, the point P2 lies along the line S1, S2, and if we want to study the path length difference, we know that delta L is equal to the difference in the path length covered by each wave. Our first wave will go from S1 all the way to P2. So this is S1, P2. This is the distance covered by the first wave. While for the second wave, we have a distance S2, P2 covered. And then this is the path length difference between the two waves, S1, P2 minus S2, P2. And if we look at the geometry that we have here, S1, P2 minus S2, P2 will give us S1, S2, which is D itself. So the path length difference in this situation is D, which is 1.5 lambda. Okay, so since the path length difference between these two sources in figure C is equal to 1.5 lambda, in order to know what type of interference we have here, let's recall the formulas for the interference. When the path length difference is equal to an integer multiple of lambda, then we have a constructive interference. When the path length difference is in the form of 2n plus 1 lambda over 2, then we have a fully destructive interference. So since we have the path length difference of value 1.5 lambda in this situation, then this corresponds to a destructive interference. The waves are arriving exactly out of phase to point P2, so we have a destructive interference at this point. And this, by the way, is the question in parts A and B. So in part A, we want the path length difference of the waves from S1 and S2 at point P1, which is on the perpendicular bisector. So here we can now say delta L is equal to S1 P1 minus S2 P2 equal to 0, since S1 P1 equals, sorry, this is P1 again, equals S2 P1, since P1 lies on the perpendicular bisector of S1, S2. And in part B, we want the path length difference along or on a point P2, which is shown in figure C. As we can see, P2 is along the line S1, S2. And like we mentioned before, we can write delta L as S1 P2 minus S2 P2. Of course, we look for the absolute value in case one of the path lengths is longer than the other. And if we check here, S1 P2 minus S2 P2 is going to be equal to D itself, which is 1.5 lambda. So we have a destructive interference in this situation. In part A, of course, we have a constructive interference since the path length difference is equal to 0. In part C, we have a circle with a radius much greater than D centered on the midpoint between S1 and S2. So this is our circle. The question, what is the number of points n around this circle at which the interference is fully constructive? So at how many points do the waves arrive in phase and have a fully constructive interference? At how many points on this circle? Now the first thing you can notice in this figure is that we have this point A here where the path length difference is equal to 0 or 0 lambda, which means that we have a constructive interference at this point. And we have also another point, so this is constructive. We have another point D over here where we can see that the path length difference is 1.5 lambda. This is deduced from the previous part in this problem, right? So here we have destructive interference. Now, what other points can we study? We can check this point. We know that at this point the path length difference will also be 1.5 lambda because we will have S2, let's name this P3 for example, minus S1 P3, and this will give us D again, which is 1.5 lambda. So at this point we will have destructive interference. At this point, so you can notice the symmetry here, this point is equidistant from S1 and S2. So the waves will arrive in phase and we will have a path length difference of 0 lambda and we will have a constructive interference at this point. So if we name this point B and this point C, at point C we're going to have a constructive interference. At point A we have a constructive interference, and at point B and D, we're going to have destructive interference. What other points can we study? So check this figure please. We said that we have this point here, point A, where the path length difference is 0 lambda, and we have this point D here, where the path length difference is 1.5 lambda, which will lead us to deducing that somewhere between these 2 points, there must be a point where the path length difference is 1 lambda. And at this point, of course, we're going to have constructive interference. So far, we've got point A with a constructive interference, point C, and point E here. And then, by symmetry, we can see that if the path length difference here at this point E is 1 lambda, then by symmetry there has to be a point over here as well, we can name it F, and a point here as well, we can name it G, and a point here as well, let's name it H, where we have a constructive interference. So we have 6 points of fully constructive interference, because between each of these 2 points, where we have a path length difference of 0 lambda and 1.5 lambda, there must be an intermediate point where the path length difference is 1 lambda. So we can now deduce that these are the numbers of constructive interference points. No other points with constructive interference can exist, because then these will correspond to a wave, to a path length difference of like 2 lambda, and this is not possible because between 0 lambda and 1.5 lambda there has to be something between them only, which is 1 lambda. We cannot have a larger path length difference. So we can now write over here our answer at A delta L equals 0, at D delta L equals 1.5 lambda. In between these 2 points there must be a point with delta L equal 1 lambda. By symmetry, we will have six points of constructive interference. And we can also note that no other points with constructive interference can exist because these will correspond to 2 lambda and above. Delta L equals 2 lambda and above, which is not possible on this circle. So we can now find that the number of constructive interference points is 6, like we said.